All right, so in this video, we're going to go through sample question 67 from the Society of Actuaries ExamP list of sample questions. The question reads, looks like a long one. A baseball team has scheduled its opening game for April 1st. If it rains on April 1st, the game is postponed and will be played the next day it does not rain. The team purchases insurance against rain. The policy will pay $1,000 for each day up to 2 days that the opening game is postponed. The insurance company determines that the number of consecutive days of rain beginning on April 1st is a Poisson random variable with mean 0.6. Calculate the standard deviation of the amount the insurance company will have to pay. All right, so this actually seems like a very easy question, at least in the beginning, from what I'm seeing. Because it's mentioning a Poisson random variable, that's the easiest one of any of those memorized random variables you have to work with. So just initially, it's telling us that we have a mean of 0.6. And I'll say this is the mean of x. I'm going to denote x to mean number of days it rains, while I will denote y to be the amount the insurance company will have to pay. All right? So the number of days it could rain. X is obviously any integer from 0 to infinity. So y, the amount an insurance company will pay, is given by this information. It'll pay $1,000 for each day up to 2 days that the opening game is postponed. So it will pay $0 if x is equal to 0, right? If it doesn't rain at all, the payment's 0. If x is equal to 1, the number of days it rains consecutively is 1, your payment is $1,000. And then your payment is $2,000 if it rains 2 days. But here's the thing, it pays $1,000 for a max of 2 days. So any time after that, your payment is still just $2,000. So anytime the number of consecutive days it rains exceeds or is equal to 2, your payment is $2,000. And now from here, we can go about calculating standard deviation. Standard deviation, very straightforward formula. The standard deviation of y is what we're calculating. That's simply the square root, the variance of y, which is equal to second moment minus the first moment squared. So we're going to need the expected value of y and the expected value of y squared. All right. Now I know Poisson random variable. It's got a very straightforward not standard deviation, very straightforward variance, but x is a Poisson random variable, y is not, so we can't use that particular rule for y. Y is just a function of a Poisson random variable. So how are we calculating expected value of y? The formula for expected value, because this is clearly a discrete distribution, right? It can't rain 1.5 days according to this situation. The expected value formula for y is equal to the sum of each value, right, each payment, multiplied by the probability of that payment occurring. And I'm just going to box this off, kind of like this. Don't want to get that confused. All right, so we should know the payments. Those are given by here. The payments will be 0, 1,000, 2,000. Okay, expected value of y is equal to a payment of 0 times the probability that your payment is equal to 0 plus a payment of 1,000 multiplied by the probability of getting a payment of 1,000 plus, I'm just going to write it down here, running out of room, 2,000 multiplied by the probability that your payment is 2,000. Now, how do we get these individual probabilities? I'm going to use just kind of a separate sheet right here because it's a little bit ripped, not a problem. Because the probability of a payment being 0 is the same thing as the probability of it raining 0 consecutive days. The probability of paying 1,000, same thing as the probability of it raining 1 consecutive day, and then a payment of 2,000, the probability of that is the same as the probability of it raining more than 2 consecutive days. So we're going to use x in order to determine our probabilities. That is a Poisson random variable. The probability of x equaling some smaller x is equal to, this should be a memorized formula for the probability function of a Poisson random variable. All of those discrete and continuous distributions, you should have those memorized, all their key important pieces of information. So the probability that x is equal to 0, right? Whatever that value is, we can substitute in there. And that is going to be e to the negative 0.6 multiplied by 0.6 to the 0 power over 0 factorial, which obviously is just e to the negative 0.6. Negative 0.6, and that is equal to 0.5488. The probability of x equaling 1 is going to be e to the negative first. Or sorry, not e to the negative first, e to the negative 0.6, that still remains the same, multiplied by 0.6 to the first over 1 factorial. That one is simply going to be multiplied by 0.6, plugging that into my calculator. I get 0.32929. Okay, just figuring out what I wanted to round to. And then the probability of x being greater than or equal to 2. Now, this is a discrete distribution. I'm not going to compute all individual values greater than or larger than 2. That's going to be impossible. The probability that x is greater than or larger than 2 is the same thing as 1 minus the probability that x is less than 2, which would be 1 minus the probabilities of x being 0 and x being 1. Okay, I'm not going to go talk about this. There's more that can be said about this, but I feel like it should already be known at this point. If you want any clarification on how I'm doing that, throw it down in the comments. I can answer it there. So all I'll do is I'll substitute in these values here and plug that into the calculator to get this probability of x being greater than 2 to be 0.1219. And yeah, I'll round there. Okay? Now I'm able to substitute. Move that up. And this will be equal to, 0 times anything is just 0, so I'm just going to kind of leave that as 0, plus 1,000 times 0.32929 plus 2,000 times 0.1219. And again, that is just something to plug into my calculator real quick. Okay, not too bad. That is 573.0 0.89, around there. And lastly, we're going to need to calculate the expected value of y squared. It's just sandpaper. There we go. I know this seems like a long problem. It is. I'm just trying to be thorough. So, the expected value of y squared, just to go a little faster, is 0 times that probability, which was written right here, 0.5488 plus, should be 0 squared, plus 1,000 squared, multiplied by that same probability of 0.32929 plus 2,000 squared, multiplied by the probability of 0.129. And that is just something to plug into the calculator. And making sure I have the numbers correct. Yes. Okay. There we go. So 1,000 squared plus and like I always mention, I don't do the problems beforehand, just so you can see me solve them as you would on an exam. I think that's important. Point 0.1219. Oh, that's an even number. That is 816890. Okay. And what we can now do is substitute into our equation for expected value. So, equation for variance. Variance of y is equal to expected value of y squared minus the expected value of y. And I'm just going to go straight to plugging this in. And that's equal to, making sure, 488,457.8519. In order to get the standard deviation, all we do is square root that number. And we get 6988.89. Our answer choices are integers, and that rounds to 699. Answer choice B. Okay. I mentioned this was an easy problem at the beginning, yet this is probably one of the longer explanations I've put. There was quite a bit to it. So it started off just giving us a payment structure, not one of your standard, limit and losses kind of thing. I suppose the limit was $2,000, right? No, it's a standard limit of $2,000. So it told us our loss was basically a Poisson distribution, limit of 2,000. And what we had to do is then identify, okay, what is the payment structure? I set up this piecewise function. I'm sure some other people, you could set up a table instead. And then from here, I just calculated expected value and calculated from there variance and standard deviation. If it hasn't become clear, if you're doing all these problems in kind of order, knowing how to calculate and apply the general formula for expected value and for discrete and uniform distributions is critical. It's how you get literally anything else to do with variance and standard deviation and required for other things, coefficient variation, any of that stuff. Like, just you gotta know how to apply the general formula for expected value for the discrete and continuous and multivariate cases. Okay? If you have any questions, throw it down in the comments. I'll answer to the best of my abilities. You want to see more problems like this, I got a playlist. And if this video helped you out, hit the like button, subscribe, because that totally helps me out. But other than that, good luck.